So Matteo Sommacal, group information scenarios for focus on NLS is parabolic initial.
So good morning, everyone. So I will be talking about curious work on a very famous set of initial data, which is this parabolic initial data. and it's good to speak after Dimitri and Amin, because I will make references. So this is a working collaboration with Francesco Demontis from Cagliari, Ortenzi from University of Turin, and Giacomo Roberti here from Northumbria University. That has recently appeared on Schr. So this is just beginning over what Amin said. We eventually all go back to NLS, and which is sort of really source of a lot of amusement, and continues to probably amaze us. But and in particular, we will be discussing this parabolic profile initial condition, and this is a kind of old problem. So you see that the amplitude here is this kind of parabola. And interestingly enough, there is this phase here, and actually, yeah. So I can actually connect with what Amin was saying. That in fact, and this will be very clear here. So the phase will play a role in a kind of important one, very relevant one, in triggering different behaviors. So it's not the same to have alpha 0 equal to 0 or different from 0. And clearly this parabola here is defined as this kind of compact support. And I will borrow terminology from optics, calling this kind of phase parameter alpha 0 as the chirp. And so what's interesting in this kind of problem we all know to be elliptic is that the endpoints of this compact support are vacuum points, so more like parabolic points. So we have this kind of catastrophe of the gradient at the spots, but the initial condition is continuous. And as I said, this is a very old problem. In fact, so it dates back to Talanov. And some people refer to it as the Talanov problem. But then it was very deeply studied by Northumbria and Strasbourg in the early 1970s. And in connection with modeling the interaction with of parabolic radio beams with the ionosphere. And it's known, and it's a recent result by Talanov that the zero chirp. So in the zero chirp case, the modulation stability is the formation of a region of strong linear oscillations. But this problem appears somehow magically, not exactly that one, but summoned in a nice, interesting way in mean field games with negative coordination. I'm not an expert on that, and this is in connection with hydrodynamics. And this is a recent work by Boboneman here. And the focusing case of this problem is a very well-known problem. So it has been widely and deeply studied. It's in the context of Thomas Fermi approximation of the Gross-Pitagoric equation for Bose-Einstein condensates. And I will refer now and then to the focusing case, in fact. So and I will. So the title makes reference to scenarios here. So I will explain here a little bit what we mean with the scenarios. And for NLS, so when you have smooth data, so we have a smooth envelope, which is not our case, but so in that case, so we have what we called the Bertollet-Obis scenario. So in particular, so we have that this classical modulation stability leads to the exponential growth of small long-wave perturbations, but this is counter-affected by this nonlinear effects. So you would have this kind of gradient catastrophe eventually for finite time, but this is, as we know, eventually regularized by effect of the dispersion. and actually this leads to the emergence of coherent structures, and in particular to peregrine solitons in the semi-classical limit. And these are pictures kindly borrowed from the work by Talanov. And another scenario for which you have that has been studied, and we refer to this as the EKT or L-Kami-Stubbs scenario, is when you are dealing now with an initial condition that features a sharp discontinuity in the amplitude. So sort of Riemann problems, and in particular, so you can think of the box problem. And so there, what is observed is that you have so what is called the dam break, in fact, in particular, the symmetric for the box, the symmetric dam break problem, which is a sort of a elliptic counterpart of the DFW that you have in the hyperbolic defocusing regime for limits. And so, in particular for the box problem, so you have like a classical regime. So there's two flows. They counterpropagate from the edges of the box, and they interact. So they form a lattice of modulated large amplitude breathers, and so they eventually interact, so to form like a higher peak in the center. And this is the problem. So in the case of this problem here, so we are not exactly in either of both scenarios. Because we have like, yes, a continuous solution, but this is not smooth. And yes, we have like this gradient catastrophe at the endpoints of the interval, where the initial condition is not zero. And so it's not exactly one of the two. And in fact, so I would like to convince you that there is in fact an interplay of these two scenarios in this situation. And this in fact can be somehow controlled by looking at the amplitude and the chirp of the initial condition. So you can play a little game here and control these two parameters and play a little bit with these two scenarios. And interestingly enough, the analysis is it's mostly numerical at this stage of the work, but so you have like a nice counterpart of this problem, which is the dispersionless case, and this provides a lot of information, in fact. So you first of all reduce the problem to the classical hydrodynamic form, and so you apply the classical Madelung transformation, and then you are returned with these two nice equations, and you have this initial condition now for the initial condition that we set, where x now is defined on this component support. And then if you set epsilon to 0, so use this parameter that controls the dispersion, so you are left with the geometric optics elliptic equations for the dispersionless counterpart. Okay, and so these equations are being subject of major studies in the last 60 years, and in particular, so for a genetic initial condition, so classical approach is the one suggested by Greenwich and Schwarzburg, and this is to apply actually an holographic transform. You can convert this problem into a linear system for these inverse functions. Okay, but this is not what we are doing here. And so in 1965, Talanov observed that there's in fact a class of very natural functions that can be used to actually study this problem, and so this sometimes is referred as self-similar solutions. And I will describe a little bit better there, because in fact one of the things that we do is to generalize lightly, so it's like a minor improvement there of so this approach, which is pretty much already everything in the work by Talanov. So and probably some of you are familiar with this result in a paper by Greenwich and Schwarzburg of what happens in the case of zero chirp. So, and for this specific choice of the amplitude, and so the self-similar solution features a blow up fine time, and this is beautiful. But in fact, so the problem was studied in like a more extensive way, and this is not, it's a little bit scattered in the literature, and is all well condensed in this book, which I understand is not available in English, and so I have to we have to thank Gennady for providing it in the original Russian version. So so they discussed Grevich and Schwarzburg this problem for this specific choice of gamma. So gamma is now the function that appears in so when you want to study the evolution of this amplitude here, so gamma is this function that appears in front of x. And then what they observe is that for this choice, so then you have to look at the chirp. And so a condition for two kind of behaviors can be derived. And for alpha 0 larger than 0. Yeah, that's also another important thing. So that you can have an asymptotic relaxation. So asymptotically, so your initial condition spreads out and decreases in amplitude, or you have like the effect of the focusing behavior to get a blow up at finite time. And depending on whether alpha 0 is larger than 2 or less than 2. And they provide also an expression for the time of the catastrophe. So so we actually start from this, and but first, before going into the details, so the self-similar polynomial solution, in fact, was used by Ovsyannikov to study the hyperbolic case. And so in that case, it can be shown that you always have this kind of relaxation. So in fact, one might expect that in the elliptic case, the focusing case, you always have this kind of opposite effect of having this kind of collapse. And this doesn't happen, in fact. This depends on an interplay between initial amplitude and chirp. So sometimes you have the relaxation, sometimes you don't. And then, okay, so in a recent work by Suleymanov, so there is advocating for the relevance of the self-similar solution by Talanov for the full focusing NLS, which is something that we explore by playing a little bit with the parameter epsilon when introducing it. So, so we provide this kind of closed form implicit expressions for the solutions. They are implicit, but okay, so they are still nice in a sense for a little discussion for the dispersionless problem. And in fact, one immediately observed that the case alpha 0 less than 0 cannot be obtained from the case alpha 0 larger than 0. So it's in fact, as you will see from the solution, it's a different case. And yes, so these are the two cases that you have for dispersionless case. So you have either asymptotic relaxation or blow up at finite time, and you can derive an expression for the time which you have this blow up. And in fact, you can verify that the quantity that drives, that controls the evolution is related to the amplitude and to the chirp by means of this expression here. And then in order to move into the semi-classical regime, at this level, we moved into the numerics. So, and one can show very interestingly that in fact, the dispersionless counterpart sort of drives dispersionless. Yes, it drives the evolution. So you can use it to follow the evolution of the dispersionful evolution. And on top of that, I'm sorry for this very wordy slide. So you reach a maximum in those cases where you would have in the dispersionless counterpart. So you would have a gradient, sorry, a blow up at finite time. So you reach a maximum at a time that coincides with the time at which you would have this blow up in the dispersionless counterpart. So somehow, and this mimics a lot what you observe in the Bertola-Tobli's case. It's a sort of a regularization, although I repeat, the initial condition here is not smooth, so it doesn't belong to that class. And as I said, this is the parameter that controls the evolution, and in particular the parameter. So if you have a blow up for the dispersionless case, then you would reach like a sort of a maximum that is very, very resemblant of a Rho wave. And in that case, if this quantity here is less than 0, then the emergence of this Rho wave and potentially of a higher order Rho wave. Well, so from what you saw from the dynamics, is very similar in the mechanism from what you have from the Bertolini scenario. So you have like that this raw wave appears with like minimal oscillations around where you have this peak. And in the other case, when as you increase the value of this quantity here, alpha 0 squared plus 4 gamma 0, so the evolution is more and more characterized by the formation of lattice of counterpropagating so breather-like structures that eventually interact nonlinearly and form an isolated peak at the center. So, and this is very resemblant of what you have in the L-Camis-Stockdale scenario. So there is no like sharp threshold between the two. So it's kind of a smooth process. And in any case, so you have always that the position in time where you would have the gradient catastrophe, sorry, the blow up for the dispersionless case is a very good predictor of where you are expecting to the formation of the so log wave-like solution in the dispersion full problem. The ansatz used by Talanov is this one, but in fact, this is like a more general result. So you can ask so for rho to be expanded as a series in X and and U as well, and then you can ask yourself so if you can truncate this series to get like a full solution, an exact solution, and this happens only if rho in fact is a quadratic polynomial in X and U is linear in X. This is like, and I will comment about this result later. So this is a general result, and then it's possible to show, in fact, that you can actually, without any loss of generality, transform this formulation here into this one. So you can, without loss of generality, choose omega to be 0, and so I have beta to be 0. Okay. So and then if alpha 0, so the chirp, the initial condition for the chirp is 0, then so you plug everything into your geometric optics equations, and then they yield this nice sort of explicit solution. I say sort of because then you have to sort out sigma, which depends on t, and typically, so you can write the explicit solution for this in the form t equal an expression for sigma. So ultimately, you have to invert the relation between t and sigma to have like an explicit solution for the two evolving parameters alpha gamma, sorry, three evolving parameters alpha gamma and mu for your solution to be written. And the choice of sign here really coincides with the sign of alpha 0. So you can show that in fact alpha 0 is 0. Then so you have to look at the sign of gamma 0. And then for gamma 0 less than 0, which is the only case that we will be studying here. So the solution lives on that compact support. Okay. So by holding sigma in time, so for the dispersionless solution, you can control where the solution is. And as we'll see, this in fact has a relevance also for the dispersion full solution. So and then we introduce these two parameters, A and B. And so then one can show that the dispersionless solution features a blow up in finite time whenever alpha 0 is less than 2 square root of minus gamma 0. Remember, gamma 0 is negative. And otherwise, it features this kind of relaxation in time over a long time. And so when alpha 0 is larger than or equal to 0, so you can have like an explicit expression of the catastrophe. And when alpha 0 is less than 0, so the catastrophe occurs, and this so it's three cases depending on the value of A0. It's kind of nice to show that these are like this is a continuous function of A. And this is in its beauty, beautifully displayed some cases that you have. So I remember attending like a talk by Bob Jenkins, the INI program, and so he was talking about this kind of only shape for a very similar initial condition that they had. That was like a smoothing effect of this initial parabola that we are starting from, and so you get this for the parabolic initial condition when so alpha 0 is around 1. And in this specific case, for this choice, so gamma 0 is equal to -1, mu 0 is equal to 1. So you have the relaxation whenever alpha 0 is larger than or equal to 2. And in fact, here it is. And otherwise, you have like the blow up at finite time. And then you can easily predict the blow up based on the formula we derived. And so this is like the full solution, like with all the possible cases. You see that there are very many. And then yes, typically, so except a few cases, so you have T as an expression of sigma, and you have to invert that, so it's an implicit solution overall. So in order to compare with the dispersion solution, so and we are always working with very small dispersion, so we are always in the semi-classical regime. We actually study numerically the problem, and so we in particular choose the initial condition for mu to be 1 and initial condition for gamma to be -1, and so we can play directly with alpha 0. And so in this situation, so we are in a case where, so if alpha 0 is chosen to be larger than or equal to 2, you always have this kind of asymptotic relaxation. But if alpha 0 is less than 2, then you have this kind of blow up at finite time, and this time is given by this expressions here. And now the big problem numerically that you have is how you resolve the catastrophes that you have at the two endpoints of the interval for the initial conditions, because that is like numerically a problem. And so you have this infinite derivatives at the endpoints of the support, and so you need to smoothen the square root in a way that you can control controlling it. You have to do it properly. So and then we use this little trick here, so that we express square root of 1 minus x squared to this sort of productorial of Gaussians, and then you actually truncate it to just take this number of them. And in fact, so it is possible to check that 10 of these terms here are sufficient to have like a really good approximation of this square root that is also, so here clearly you have to play a little bit, so not too sharp for the computer to deal with. So for you the numerical algorithm to deal with. So pretty much we use some spectral method, pseudo-spectral method, which is like pretty much the method of the lines. So we're evolving in time, Runge-Futa, and taking derivatives in space with fast-Fourier transforms, and we check also the power spectrum, so to ensure that the partial Fourier transform does not reach the boundaries of the spectral domain. And then what we observe is that, as I said, it is sufficient to take the first 10 terms in that expansion. We've done experiments with 15 without getting any real big improvement. So clearly you have to play also with your discretization if you start increasing the number of terms, because it becomes sharp. Your solution, your initial condition becomes sharper and sharper. And this is what you get. So in every single row you have like the behavior in the x plane. And here, so the dashed line is the initial condition, and the black line is what you get at the maximum. So sorry, here at the top, you have the information about the numerical details. So epsilon in this, all this numerical results is 1 over 15, it's rather small. And what you have here in this rectangle here is a cross section along x equals 0. So you have an evolution of the peak, really. Okay? And this is like an XT zoom, so of what happens around when you get the rolling. So here, and the red dashed line here is the contour of the is the support, the endpoints of the support for the dispersionless counterpart. Okay? So what you see here is really that this very high peak rod wave is accompanied by proportionally very small oscillations, and then in fact it's harder and harder to run numerical simulations for smaller alpha. So you can actually verify that the smaller the value of alpha, the less oscillations you get around the formation of the peak. And so this is like the base for our conjecturing claim that so here there is a sort of a Bertolli Bertolli scenario, and you see that what you get when so you increase the value of alpha larger than 0 and approximating and approaching number 2, so you get this kind of oscillations that are comparing the information rock wave are getting larger and larger. So just like 1 minute, and then you can repeat this for like smaller value of epsilon, and still you have this kind of wonderful agreement of the formation of this peak at the point where you have this gradient, so the blow up for the dispersionless solution. And this is what you have for 2 values of epsilon, even a very large one. So, and the black line is so the time of the blow up for the dispersionless counterpart, and the points are the result of the position in time for the maxima of these Rogge-like solutions in the dispersion pool case. So you see that there is like this wonderful prediction that one can do. And then yes, and this is the behavior for the dispersion. For the relaxing case, still it works. And then even for a large value of epsilon, you can still like sort of describe qualitatively what's going on. Yeah, but the larger epsilon, the worse is your switch. There are other things that can be done. I'm almost done. Sorry for long here. But so, for instance, so this result that this truncation is that you get here. So this truncation here. So it's so you get an exact solution for a truncation that stops at the second degree for rho is in fact general, and then so it doesn't depend on the number of dimensions in which you are. So in theory, so you can study this problem in more dimensions. I mean, using the same approach, and there are other questions that can be asked. Well, first of all, providing a full analytical explanation of what we are observing, and we are not there, and it's kind of hard. It might be a very hard problem. And the other thing that can be done is to apply this not only to like multidimensional problem, but going to multi-component. And this is a very natural question. So what happens if you then decide to study vector NLS? And in fact, the same theory applies. And so, but more the phenomenology there in this case is much, much richer. So you can have like relaxation in the two fields. But in fact, surprisingly, well, or maybe not. So you can take an initial condition that's an initial condition for which in one field, for vector NLS, you have what you would expect as a relaxation if it were uncoupled from the other field, and a collapse. And then if you let them evolve, then what you see is that so the field that was expected to relax is starting to relax, but eventually is dragged from the collapsing field, and then it features like a collapse as well. So, well, it's not really a collapse, but it features like a rock wave. And so this is work in progress. Thank you for your attention.
Thanks, Scott. So these Talanov types are parabolic solutions of the dispersionless problem. Each solution and it's an elliptic system. So is there some idea how we should think about that? I mean, I know of course.
Yeah. Let's talk about it because it's hard.
It's a little fun.
Yes, it is. I agree. It's hard problem is an elliptic problem with meshes.
Maybe there's something special about the fact.
Yeah. So we've been wondering around how this 2 points can be treated. Yeah. So
no, but those 2 points are on the side line. So you're not
sorry, these 2 points.
the 2 points are the side line. So
Why does that make it better?
Yeah, there's these 2 points are
So you asked, why does it make it better?
No, in those 2 points it's parabolic. It's
yeah, like with that process.
It's degenerate.
Yes.
But that makes it okay.
No, it makes a difference. It's
Yeah.
enough. Sure, it makes a difference. I'm telling you, Stefano Primo.
Yes. Yes, that's the problem. You have to connect to it. Well, everywhere else is an elliptic problem, except for ideas are very well kept.